Hey there, in this video we're going to continue our review of functions and we're going to talk about logarithmic functions. So what is the logarithmic function? And so here I have it broken down by base b, so any base really. So for any base b greater than 0, you have to be a positive number, with b not equal to 1. The logarithmic function is the log base b of x. And the important thing here is that the logarithm is the inverse of the exponential function y equals b to the x. So in prior videos, we studied the exponential functions. So the logarithms, now that we've done inverses as well, the logarithmic function is the inverse of the exponential function. And if the base is e, then the inverse is the natural logarithm function, which is y equals ln x. All right, so what does this all mean? When we have the graphs of our functions, can you pick out which one is which? Yes, so the blue one is y equals b to the x. And because this is our exponential, so this is our increasing exponential function. Now this doesn't actually cross the x-axis. It is an asymptote. So in this case, y equals 0 is a horizontal asymptote. Now the inverse functions, we can reflect it along the line y equals x. So this is the line y equals x. Remember, as we talked about in the previous videos about inverses, an inverse function switches the x and the y. So essentially you reverse your x and y coordinates. So if this is xy, then as you reflect that along the line y equals x, that becomes the point xy. So for the y-intercept, I have the point here, the y-intercept is 0, 1, and as you reflect it along the y equals x line, that becomes, now instead of being a y-intercept, it is an x-intercept. And so the x-intercept for most exponentials with no vertical or horizontal shifts is the point 1, 0. And so as we reflect all of these points from the exponential along the y equals x line, we end up with our logarithm. And so this is the function with f of x equals log base b of x. And as the base changes, the graphs of these will change as well. So you can think of when we did exponentials in the previous videos, we had graph 2 to the x, 3 to the x, and e to the x. So then how did those relate to logarithms? So you have log base 2 of x, right? That would be so log base 2 of x is the inverse of 2 to the x, and so on. Log base 3 of x is the inverse of 3 to the x, and the natural log of x is the inverse of e to the x. All right, now that we understand that logarithms are the inverses of exponentials, we're going to write our definition of a logarithm, which is going to be pretty important for us to be able to solve logarithmic equations and for all the properties. So the definition of logarithms is that if you have a log base b of a equals x, this can be rewritten as b to the x equals a. So this is the inverse property, and this goes both ways. So if you have an exponential, you can write it as a log. You have a logarithm, you can write it as an exponential. So with, say, y equals log base 2 of x, our function. So let me give it a function notation here. So if this is the function, right, then how do I find some values? So find log base 2 of, say, 8. So how do I find that? Well, according to my definition, I can say, well, I don't know what it is. So let's say log base 2 of 8 equals x, because I don't know what it is. Now that definition allows me to say 2 to the x equals 8. So essentially, what exponent do I put on 2 to get 8? So that's a quicker way that you can read a logarithm when you see something like this. What exponent do I put on the base to get 8? So in this case, x will be 3. The other way that you could do it is try to match the bases. So I can say 2 to the x equals 2 to the third. And as long as the bases are the same, then the exponents have to be the same as well. And so I can do it for any logarithmic function, right? So if I have g of x equals log base 5 of x, right? How do I find log base 5 of 1 over 25? So this means what exponent do I put on 5 to get 1 over 25? And that will be negative 2. But you can translate it into an exponential by saying 5 to the question mark, or you can call it x, equals 1 over 25. And then rewrite it some more. 5 to the question mark equals 25 is 5 squared, right? So then this will be 5 to the minus 2, which means that question mark is negative 2. So log base 5 of 1 over 25th is negative 2. So the logarithm is the exponent. What exponent do you put on 5 to get whatever value x is? All right, so now that we know that, let's try this example. We have the graphs of log base 2, log base 4, and log base 10, and we want to match the curve to the function. So here, I got rid of the stuff that was in the background for some reason. So here, let's look at this. Notice that all of them have an x-intercept of 1. So what this means is that, what is that point? This is the point x is 1, y is 0. So if I look at y equals log base 2 of x, right? 0 and 1, if I plug it in here, that means that when x is 1, y is 0. So I'm going to have 0 equals log base 2 of 1. And so that makes sense. If you translate it, if we use our definition of logarithms, this will say the base, so 2 to the 0 equals 1. And that is a true statement. And so for log base 2 of x, so which one is it? So here's 2. So I'm going to go, okay, so when x is 2, what's y? So plug it in, right? So I'm going to have, I know y equals log base 2 of x. So I'm going to have, I don't know what y is, so leave it. Log base 2 of 2. I'm saying when x is 2. So what exponent do you put on 2 to get 2? And that would be 1. So when x is 2, y is 1. So that will be this function. Right, and so based on the base, I can kind of go off of that. So now I know that for this one, log base 2 of 2 is 1. What about for log base 4 of x? When am I going to get 1? I know log base 4 of 4 is going to give me the y value of 1. So one way I can think about this example is, here's y equals 1. So if I extend this line all the way, right, notice that I hit the pink graph at 1, 2, 3, 4, which makes sense with this. Log base 4 of 4 is 1. So that must be log base 4 of x. So I can the names here. So for this one, for the black one, I'm going to have, this is y equals log base 2 of x. And then the next one, this one's going to be y equals log base 4 of x. And so the blue one must be log base 10 of x. And the reason for that, we can even see if I use my, put in x in there, what exponent do you put on 10 to get 10? That's going to be 1. And so notice that 10 is out of the frame here, that this is x equals 4. So 10 is going to be somewhere over here, And so the bigger the base, the slower the function grows, right? The lower, the closer to the x-axis the function is going to be. So it makes sense that this one then is y equals log base 10 of x. And so that's how we can start finding values for this function. You could do a t-table as well, and then keep using the definition of the logarithms, right? So if I wanted to do it for log base 10, since I'm using that one of x, then I will have x and y. So I will start with, well, could you have x equals 0? No, right? So notice that if you have 0, what exponent do you put on 10 to get 0? That's not possible. So we say not in the domain. So notice that the domain, by looking at the graph also, the domain of all these logarithms is 0 to infinity. And remember when we were doing inverses, or when we were doing exponentials, the range of an exponential was from 0 to infinity. And now that we know about inverses, right, the range of the inverse is the domain of the function. So the range of the exponential, 0 to infinity, is now the domain of the logarithm. So I'm going to make a note there. The domain is 0, not including 0 to infinity, because we can't take the log of 0. And so going back to our t-table, the first number I can start using is 1. Log base 10 of 1, as we see here from the graph, is 0. And then I will probably want to be a little clever about how I do this. Because it's base 10, I'm going to then choose 10, 100, 1000 powers of 10, right? So as you can see, this is going to be a very slow growing function. Log base 10 of 10, what exponent do you put on 10 to get 10? 1. Log base 10 of 100, what exponent do you put on 10 to get 100? 2, and so on. And the same thing you could do to get a negative number, right? 1/10, 1/100, 1/1000, and so on. So that's how you can use a t-table as well. All right, let's now look at the inverse relation here and the rules of logarithms. So if I have, because I have an inverse relationship between exponentials and logarithms, there are some logarithms that become pretty nice to compute because of that inverse relationship. So the first rule is that if you have the base b raised to the exponent of the log base b of x, you just get x again. And this comes from when two functions are inverses, right? So f of x and f inverse of x have the property that f of f inverse is x and f inverse of f is x. So that's what's going on here, right? If I have f of x is b to the x, then f inverse is the log base b of x. So when I do f of f inverse of x, what does this become? That's going to be b to the x, but we're putting in f inverse. So it'll be to the log base b of x. Since these are inverses of each other, this property is valid. So this is going to be x. And likewise, if I do the other way, right, f inverse of f of x, now into f inverse, so log base b of x, so in place of x, I'm putting in f of x, which is b to the x. I'm going to get x. So essentially when the bases match, you just get whatever the exponent is. So an example of this will be if I want you to find 5 log base 5 of 7, right? Because I have 5 as the base of the exponential, but it's raised to the log base 5, here I'm just going to get 7. And similarly, if I have the log base 10 of 1000, what's that going to be? Right, this is log base 10 of 10 to the third. So the bases match, so this is just 3. So I just get the exponent back. And the natural logarithm, natural log of x, is the inverse of e to the x. right? Those are inverses. So if I have natural log of e to the x, I'm just going to get x. So what I want you to remember is that the natural log of x, you could rewrite it as the log base e of x, so that then you can see it a little better. So this will be the log base e of e to the x. And so now you can see, since the bases are the same, they're inverses of each other, you just get x. Let me go back to the rules, the properties of logarithms. Now, because logarithms are essentially exponents, a lot of the rules between exponentials and logarithms are the same. So in exponents, right, when you multiply the same base, you add the exponents. So here we have the same base, and the inside of a logarithm is being multiplied. So the rule is that you have then here the log base b of x plus the log base b of y. So when you have the same logarithmic base and the insides are multiplied, you can write it as two separate logarithms added. And subtraction works the same as with exponentials, right? When you divide the same base, you subtract the exponents. So this is going to be log base b of x minus the log base b of y, and then the power to power you multiply. So with logarithms, when you have this log base b of x to the y, what we're going to do is that exponent, we're going to multiply it by the whole thing. So essentially the exponent comes to the front. So it'll be y times log base b of x. And this one is that property, the inverse property, log base b of b. There's a 1, an invisible 1 in there, so that's just going to be 1. So the main properties to remember are these three, L1 through L3. Those are properties of logarithms that you really want to make sure that you know. As we get into chapter 3 and we start doing derivatives with logarithms, these properties are going to become really important. Let's try an example. So use properties of logarithms to expand that quantity. So let's see what's going on here. So I have log base 4 of stuff. And inside there is multiplication, there's division, there's a radical, there are some powers. So we have pretty much all the properties in here. So let me move this up so I can see the properties. All right, so we're going to expand it. And how do I do that? So the operation that jumps at me right away is the fact that there's a big division there. So that looks like L2. So I'm going to say this is so log base 4 of x squared y over the square root of z. I'm going to raise the square root of z as z to the 1/2 equals. So using the L2 property, this is going to become log base 4 of x squared y minus log base 4 of z to the 1/2. And now I keep going. So now notice on the inside of the first quantity, I have a multiplication, x squared times y. So I'm going to use L1. So this is going to become log base 4 of x squared plus log base 4 of y, and then minus log base 4 of z to the 1/2. And lastly, we're going to use the power rule, L3. When you have an exponent, you can bring the exponent to the front and multiply it by the logarithm. So that's what we're going to do with the exponents. So I have 2 is an exponent and 1/2. So those are going to come to the front. So I'm going to have 2 log base 4x plus log 4 of y minus the log base 4 of z. Oh, and bring the exponent to the front, 1/2. And is there anything else that I can do? No, I've used all the properties. So that's as far as I can go. One thing of warning, so my warning here, is if you have, for example, I want you to expand the log base 3 of x minus 1 over, let's say, y. right? What are the properties here? So I can say, well, I have the division, so then this is going to become log base 3 of x minus 1, and then minus log base 3 of y. Now, this x minus 1, be careful not to say, oh, log base 3 of x minus log base 3 of 1, because that is not a property. Notice that in here, our properties are x, the inside of the log, x times y, x divided by y, or x to the power of y. There's no property that has log of base something, and the inside has a plus or a minus. So the pluses or minuses are just on the outside once you're expanding and you have multiple logarithms. So when you see this, log base 3 of x minus 1, there is nothing we can do. This cannot be expanded anymore. So my warning is, right, the log base 3 of x minus 1 is not equal to log base 3 of x minus log base 3 of 1. So be careful about that. Properties of logarithms are really helpful because they help us solve equations involving logarithms, and they help us also find domain and all this fun stuff that we've been doing. So let's try an. Let's say I want to solve log x plus 2 plus log x plus 5 equals 1. Okay, so how do I solve this? Well, first of all, when you don't see a log, so if it's just, like in this case, log of x plus 2, what does that mean? What's the base? And it is understood, is what's it called, convention, that when there's no number there, it is log base 10. Kind of like when you have the square root of 4, right? There's no 2 in there. The index, we don't write the square root of 4. We don't write the 2 in there. So when there's nothing in there, convention lets us know that that's the square root. And as soon as there's a number in there, now you have an index for the radical. So same thing for the logarithm. When there is no number there, that is convention log base 10. So these are both log base 10. So how do I solve it? Well, in order to use our definition of the logarithm, which was where? Where did we put it? Right here. Log base b of a equals x. To change it to an exponential, I have to have a single logarithm in order to be able to use this definition. So the first thing with an equation like this is write as a single logarithm. So that will be our first step. So I'm going to use then the first property of 1 and backwards. So these equals go both ways. So if I have a logarithmic expression expanded, I can condense it into a single log by reversing the property. So here I have it expanded. So we want to write it as a single log. So how do we do that? Use the property in reverse. So this is going to be log of x plus 2 times x plus 5. Right? The property says when there are two, when you're adding, you can condense it into a single log by multiplying, equals 1. And so you can simplify this. So this becomes, what is that, x squared plus 7x plus 10 is equal to 1. And now I have just a single log. So now I can use my definition that log base b of a equals x means, and again, forwards and backwards, b to the x equals a. So I can use this to say, okay, b is 10. So I'm going to have 10 to the whatever's on the other side of the equals, right? The x is on the other side of the equals, so 10 to the 1 equals, and then the a. The a is the thing that I'm taking the log of. So x squared plus 7x plus 10. So 10 to the 1 is just 10, so I have 10 equals x squared plus 7x plus 10. And subtract 10 from both sides, right? I do have a quadratic, So I have to set it equal to 0 to solve. And so I have this equation. Then I have 0 equals x squared plus 7x. My font color didn't change. And now I factor out the x. So either x is 0 or x is negative 7. And with logarithms, it's really important that we check our solution because, as we saw with the graphs, the domain of the logarithms is from 0 to infinity. So you cannot take the logarithm of a negative number. And so here we worry that as we take these values, now it doesn't mean that x can't be negative, it just means that the inside of my original logarithmic expression can't be negative. So for example, if one of my answers was negative 1, that will be okay, right? Because minus 1 plus 2 is 1. Minus 1 plus 5 is 4. So I can take the logarithm of those numbers even though x is negative. But in this case with 0 and negative 7, probably not. So our expression was log of x plus 2 plus log of x plus 5 equals 1. So when x is 0, let's see, log of 0 plus 2, that's 2, plus log of 5 equals 1. So these seem to be okay, right? We can do the property now. We have two logs, you can multiply them into on the inside of a single logarithm, and I have log of 10 equals 1. And that's true, right? Because this is a log base 10. And so that checks. What about when x is negative 7? When x is negative 7, I have log of negative 7 plus 2 is negative 5 plus log of negative 7 plus 5, that's negative 2. And this already does not work, right? We have a not possible. You can't take the log of a negative number. So negative 5 and negative 2, not in the domain. So we can't do that. So our only answer will be x equals 0. Now, I just want to emphasize again, x can be negative. It's just when you check it, the inside of the logarithm can't be negative. Right? Think about what I said earlier. If x was negative 1, this will be totally okay. So x equals negative 1 will be a solution. It's not, but hypothetically. All right, I'll end logarithms with that. And email me if you have any questions.